Hi guys, we're going to be talking today about rates of reaction. At the moment you've got to the first part of the second year. You're going to be looking at Module 4. Module 4 is looking at physical chemistry, which is things like rates of reaction, a bit more equilibria, something called entropy, some electrochemistry, and some inorganic chemistry, so talking about complexes and things. You're then going to be doing Module 6, which is going to be the last module, which is Advanced Organic Chemistry. Did I say Module 1, 2, 3? This is Module 5. There we are. Today we're going to be looking at rates, and this is the sort of the start. You should have already done, in fact earlier this week, some spreadsheet work to teach you how to use spreadsheets, how to plot graphs and things. I've got to say this is a skill you really need to get into, because if you can get into this skill, it will really help you when you're doing practicals, because you won't have to sit there plotting graphs by hand. You can use Excel or another spreadsheet to do it, and having that skill will really help you when you go to university, but it's also a requirement of one of the PAGs. So what I'm going to do is flick to the PowerPoint and we can get going. So we're going to be talking about orders, rate equations and rate constants. Today is a case of really just getting you the language which shows you how to work through what you're doing. You're going to be able to explain what the rate of reaction is, what the order of a reaction is, the overall order, and what the rate constant is. We're also going to show you how to work out what the rate constant is, how to work out what the rate equation is. Essentially, it's doing what you've already done, but turning it into a little bit of maths. And we love a bit of maths because it means we can model what's going on and things like that. These are the key words, and it's really important you have a look at these key words. In the next couple of slides, it defines them, but I'm not going to dwell on them. I would say making flashcards would really be helpful for you, but I'm not going to explain all the way through them because that's basically the point of the PowerPoint going ahead. But always go back, have a look, and see if you can define them. Remember that the PowerPoint is available on Moodle to help you. It's also available on your OneNote book. It's been put on there by, I think Nick and Judith have put it on there, so it's really worth having a look. So this is the first set of key definitions. As I said, I'm not going to dwell on them. I'm not going to talk about them, but feel free to pause them if you need to copy them onto some flashcards. Knowing them is really important because you need to be able to confidently use these phrases like rate of reaction, what the initial rate of reaction is, what the equation is, and the order. More definitions here. Again, you have to make sure that you're able to talk about them because they make great fodder for a 6-mark question. I think I'm about to sneeze. No, it's gone. Don't just hate it when that happens. So, back in GCSE and last year, we spoke in detail about the effect of certain things which change the rate of reaction. They were temperature, pressure of gases, concentration, catalyst, and surface area of solids. Those 5 things you have to know how they affect the rate of reaction and why. So what I'm going to do is just revise them quickly with you now. It might be a case, actually, you might want to pause this video here and draw out how each of those things work, but we'll sort of do that now. So let's have a look at surface area of solids. So if I have something like a big cube here, and I sort of draw said big cube, and we'll say that that has a surface area of 2 by 2 by 6 because there's 6 surfaces on there. We're only looking at the surface area, so we are 2 times 2 times 6. That makes 4 times 6, which is 24. So my surface area would be 24 centimeters squared, for example. Now, if these were sort of those little blocks that you used to be able to get in maths, I don't know if you guys still have them. We used to sort of be able to construct shapes with these little blocks. And if I took all those blocks apart, so if it was made of 1 centimetre cubed cubes, let's have a look what happens if I take them apart. So if I turn it into 8 1 centimetre cubes, because there's 1, 2, 3, 4, 5, 6, 7. Oh wait, 1, 2, 3, 4, 5, 6, 7, 8. I'm starting to. It's too early in the morning. So we've got 8 of those, and they are 1 by 1. And if you think about it, so it's 1 times 1 gives you the area of the square, and there's 6 of those squares on a cubes. So it's going to be 6 centimetres squared per block. Now I have 8 of those blocks. So I can see that actually just by splitting it up, I have more surface area exposed. So if we think about it, any chemical reaction happens when two particles collide with sufficient energy in the correct orientation to react with each other. If they do that, they might react with each other, and we end up getting a molecule formed, for example, and this is very sort of simplistic. If there are more surfaces for the molecules to react, the rate of reaction will be faster. So that's how that works. If we break down and we increase the surface area of something by crushing it up or making a nanoparticle or something like that, the amount of surface available for reaction increases, so therefore we increase the rate of reaction. Let's have a look at concentration. If I have a box here, rates, everything's in sort of boxes. If everything is moving around randomly, so if I have 2 particles in here, and that's not very well, if I have 2 particles in here, and we'll have one of them like this, and they're just moving at random directions, or in this box, if I have 1, 2, 3, 4 particles, if they're just moving around in random directions, we can see that the chances of one of these particles reacting with the other one is going to be higher in this case here. So we can see that concentration, or it's exactly the same as pressure, will affect how often these particles collide with each other, which will affect how often they can collide with each other successfully, which will affect the rate. So if we increase the concentration, we increase the chance of those particles colliding with each other successfully and reacting. So that's concentration. Now, what about a catalyst? A couple of things we can draw here. We can draw what a catalyst looks like. Remember, in catalysts, what will happen is it will immobilize and adsorb a molecule, and what will happen when it's adsorbed it will change the energies, and it will cause, for example, the molecule to split apart or 2 molecules to meet. The way it works is if I have an exothermic reaction, any exothermic reaction, or endothermic reaction in fact, if this is your activation energy, so this one here, what we'll see is that is our activation energy without a catalyst. If I have a catalyst, it provides an alternative pathway to the reaction. So what we'll see is this alternative pathway to the reaction will have a lower activation energy. Now, if we look at our Maxwell-Boltzmann distribution, which is the distribution of molecules over a temperature, so it's distribution of energy of molecules over temperature, and essentially it is the population of molecules, and then we've got some energy function here. Normally, what it would look like is this would be our sort of distribution of molecules, and our activation energy, for example, is here. So that means that all of these molecules that are over this energy are available to react. So this is without catalyst. We know that adding a catalyst lowers the activation energy. So if I put the activation energy down here, so the one with the catalyst is down here. Ooh dear. There we go. EA with a catalyst. It's been written for me. We can see now not just these ones can react, these ones can also react. So if there are more molecules available for reaction, it means that given the same conditions, you will have more reactions happening, which means that we will have a higher rate of reaction. Pressure, I'm not going to dwell on, apart from to say it is very, very similar to our concentration. Essentially, it's concentration in a gas, and more particles there available for reaction means that they're going to collide. What I will say, though, is if I have a Maxwell-Boltzmann distribution, it's not going to affect the shape of it. It will sort of still stay the same shape. However, if I have more particles, what it might be is it may increase the height of that curve, which again will mean if this is the activation energy, we have this number of particles available at our lower pressure or concentration. If we increase the pressure or concentration, which means we have more particles, that means we have more particles available, which means that our reaction will happen more quickly. What about temperature? Temperature is a nice one. We have our particles moving around. What I'm going to do is I'm going to put deliberately just a couple of different particles in. These particles are moving in random directions. So if we send this one off in this direction and we send this one off in this direction, what will happen is it will move at a certain speed. If I increase the temperature, it will cause the kinetic energy of the particles to increase, which means that they will move more quickly. If they move more quickly, it is more likely that they will hit each other. And if I look again at the Maxwell-Boltzmann distribution, if I have, I'll put an N on here and an energy here. If I have this, our standard temperature, and if we have this as our activation energy, so here, if I do it at a higher temperature, what it will do is it will change the average energy of the particles, and it will cause the Maxwell-Boltzmann distribution sort of flatten out slightly. And if you think about it, because of that, that's not the best. Oh dear, that really wasn't a good idea. Because of that, in the second case, instead of just having this portion reacting, this portion here can also react. That's definitely not the best Maxwell-Boltzmann distribution that I've ever drawn. I think it's more just the fact we're sort of getting there. Okay, so calculating rate. We know what changes the rate of reaction. We have to talk about how now that we calculate rate. How now we calculate rate. Oh dear. So, rate can only be found by actually doing the experiments to find them out. We can't just look at the chemical equation. Even if there is something that says, okay, if you do this, the reaction will happen at this rate and things like that, it is likely that that has been determined in the real world. People have done experiments to do that over certain conditions and things. If we look, this is a very GCSE idea, that the rate is equal to the change in concentration of reaction or product. So that can either be a product being made or a product being made or a reactant being used up, divided by the time taken for that to change. And if you think about that, if that time is in seconds, which it's an SI unit, so we would normally be looking in seconds, we can have moles per decimeter cubed per second. If you look at something rusting, for example, it's more likely you're talking about hours, days, weeks, or years. But normally in the lab, anything we're talking about in seconds. as you saw in the last module, not the last module, the module where you did equilibria, concentration of a component of reaction, so if I have A plus B becomes AB, for example, if I wanted to know what the concentration of reactant is, this A, we denote it in an equation by these square brackets. So the square brackets mean concentration of A. Okay, so it's really important you understand that's what those square brackets are for. And get used to that, because it's not just going to be in rates, it's also in equilibria, and it's going to be in pH and lots of things going forward. So understand that those square brackets mean that we're talking about the concentration of something. If I wanted to look at the concentration of B, it would be like this, concentration of B. And if I wanted to have the concentration of the molecule that's come together, it would be the concentration of AB. So that's how we express that mathematically. So when we're looking at the, for example, the decrease in the concentration of reactants, what we do is we look using experimental data at what the concentration of the reactant is. That could be looking at colour, that could be looking at the concentration of something, how coloured something is. We would look and we'd see, for example, a colour disappearing, and we could see the gradient moving like that. If I wanted to know what the rate was at any particular point, I would have to take a tangent. We can see this is a tangent. The tangent is where it touches the line right at the point you are, and then we look at the difference in y divided by the difference in x. So a tangent is going to be dy by dx, which is, for you maths bods out there, or the difference in y divided by the difference in x. Again, this is a skill you should have got at GCSE. So talking more about the tangent, we have to make sure when we're drawing tangents that the line only touches the curve at the point that you're looking at the rate being measured at. Well, that's a great tangent. That's probably one I drew earlier and saved by mistake. We can see here, where does that tangent touch the line? That touches it right at 0. So this would be a tangent of the initial rate. And I've got to say, most of our measurements, excuse me, I've moved from my desk because it's sort of being used. Most of the measurements are taken at the initial rate, so as early in the reaction as possible. So you can see this one here, it doesn't quite look like the tangent you'd normally see, but it starts right at the initial rate and it sort of gets further and further away as we go along. Have a think about why the line of a reaction, so the concentration of the product, sort of starts to flatten out after a while. We'll maybe talk about it a bit later. So, in page 7 of your booklet, you will see that there are some graphs. Try and draw some tangents on there. Really, really important to give it a go. It is a real skill. It's something you can be asked to do in the exam. Ooh, and that's the answers for it. Okay, so we have 4 reactions here. How would we work out what the rate of reactions are? So if I look at this top one here, I have a solid and an aqueous solution, and I'm making a gas and an aqueous solution. So how could we work out what the rate of reaction is here? I would say really important to look at the state symbols here. If we're looking at this one here, it's giving out a gas, so we can collect the gas. There is another way we could do it, which is to weigh the mixture as it's reacting and seeing what the loss in mass is. The thing is, though, if you think about it, for this is such a light gas that actually it'd be very, very difficult to measure all of the gas that's given off particularly accurately, unless you have very, very expensive scales. I would always say it's much better to just measure the volume of the gas, because whilst it's a very light gas, it has the same molar volume as any other gas at room temperature and pressure. Let's have a look at this second one. I've got silver nitrate plus sodium chloride, and it's making silver chloride and sodium nitrate. Silver chloride is a solid, so how would we do this? With this one, I would say something like a disappearing cross reaction. If you remember, probably at GCSE, you had the conical flask, has some sodium thiosulfate in it, you put a bit of hydrochloric acid in it, and then you judge when the cross disappears. With this one here, again, you could look to see either how long it takes a precipitate to form, or we look to see how long it takes for the cross to disappear or something like that. This one here, slightly different. You can't just look at the states of matter like we did in this one and this one. With this one, we have hydrochloric acid plus sodium hydroxide, which is a base, and it's making sodium chloride plus water. If we think about it, actually we could follow this reaction by looking either at the pH, or we could look at the concentration of these things by titration. So measure the pH change by meter or titration. This reaction does actually happen pretty quickly, so we wouldn't expect that to change very much, but there are going to be some other acid-base reactions which do take a while to happen. So this idea of measuring the pH change is really, really important. pH meters are things that you've not really used at the moment, but pH meters can very accurately tell you very small changes in concentration of acids and alkalines. What about this one here? We've got some aqueous chlorine, which probably get from bleach or something. I've added some sodium iodide, and what it's making iodine solution and sodium chloride. So iodine solution, what do we know about iodine solution? Does anyone know what colour iodine solution is? Iodine solution is a very dark brown solution. Remember, we're talking about the solution, not the actual pure solid, because iodine is a solid at room temperature and pressure. It's brown. So we can actually change or look at the colour of the solution, because if you think about it, if I have a very small amount of iodine in there, the brownness is not going to be particularly dark, whereas if there's a very high concentration of iodine in there, it's going to be very dark. You could look at the chlorine, but chlorine is very pale green, so it's very difficult to look at, but we can look at the formation of the iodine. Another way of doing it is by something called a redox titration. So, we've spoken about how we can follow reactions. Now we have to talk about the order of reaction. So, when we do a chemical reaction, not all components in that reaction work equally. If you look at organic chemistry, for example, if I have something like the addition of HBr to an alkene, you note that actually that there's a couple of different distinctive steps that happen in that reaction for it to be effective. One of those steps is going to be a lot slower than the others. That is called the rate determining step, and it's something which we'll get onto later. But if I had several components in a reaction, some of them are going to be more important for that rate determining step than others. Some components in that reaction may not take place in that rate determining step. So when I say rate determining step, it is the slowest step of the reaction, and it sort of determines how quick the reaction happens. So with how important a component to a reaction is to the rate of the reaction, or the rate determining step, we can assign an order of reaction. I know I'm being a little bit cryptic, but we will be doing a lesson on what order of reaction means and how we can work out mechanisms from orders. So I'm sort of going over it I'm brushing the surface of it rather than doing it in detail. So If a component in a reaction does not take place, or doesn't take part in the rate determining step, so that slow step, it is zero order, because actually its concentration in that slow step does not matter. It's not going to change the rate of reaction. If one of them takes place in the rate determining step, it would be first order. And if two of those components take place in the rate determining step, it's going to be second order. So what we're saying is, for that reaction to happen, actually, we could take the concentration down really, really far on something that's zero order, and it's not going to particularly change the rate of reaction. So if we look at our rate equation, and at the moment we're just saying rate is proportional to the concentration of a component A in a reaction, this thing here is the order of reaction. So if you think about it, if I have component A, for example, and it doesn't take place, it doesn't sort of take part in the rate determining step, if I have rate is proportional to the concentration of A to the power of 0, so 0 order, actually the rate is just going to be proportional to 1. So it means it's not going to take part in the reaction. If I have rate is proportional to concentration of A and it's a first order component, it's going to be rate is proportional to the concentration of A to the power of 1, which means that rate is going to be equal to a constant times A. If it's second order with respect to A, it's going to be rate is proportional to concentration of A squared. So it's really important to understand that actually this is going to influence the rate of reaction, and how it influences the rate of reaction is the order. Now, we determine the order normally experimentally. So we do equations, or we do experiments where we change the concentration of certain components, and if we plot how that changes the rate, we can work out the order of reaction. So if I have a zero order, that means that concentration has no effect on the rate. So the concentration over time looks like a straight line. It will always be a straight line. And remember, this is concentration against time. You will have a slightly different one, which you have to learn later. So this is always a straight line, and you will be asked, this is a good multiple choice question. They show a concentration against time graph, and they say, okay, what is the order of the reaction with respect to this? So we can see that it is a straight line. If we have a first order, we can see that its rate is proportional to the concentration of A to the power of 1. So if A doubles, then the rate doubles. If A triples, the rate triples too. We can see that the line looks more like this. It's a nice gentle curve. And as concentration halves, the rate halves. So it goes down like that. It's an exponential relationship. It is what you'd get your half-life graph from if you're doing sort of physics and looking at something that's radioactive. Second order, the rate equation looks more like this. Rate is proportional to the concentration of A squared. And we can see it's very different from the other graph. The other graph, the first order graph, was very, very gentle, whereas this has a very steep curve going downwards, and it sort of very, very slowly decays to 0. So if I doubled the concentration of something that's second order, it would mean that the rate quadruples. If I times it by 3, the rate times by 9, because if you look, it's this squared relationship. So if I times by 3, it increases the rate by 9 times. So the difference between that other graph and this graph, that other graph, the first order graph, is a lot smoother, so remember that. And remember, the zero order graph is a straight line. So, have a look at the textbook, pages 8 and 9. It is available on Caboodle at the moment, or we are looking at getting it elsewhere so you get them back. But have a look at the textbook. Label the rate equation. Write it down and label it. I'm going to give you a moment to do that, but I am going to go through what you should be getting, and my foot's going numb now. Ah! Okay, so R is equal to the rate. So the rate is essentially what we calculate from experimental data. And in this case, the rate is moles per decimeter cubed per second. You think it's concentration divided by time, so it's always going to be moles per decimeter cubed per second. K is the rate constant. We had the rate is proportional to the concentration of A, for example. Because we put it's proportional to, that means in order to turn it to an equal sign, we have to make a constant. Now, this constant is different for every reaction, and it's different for different conditions in a reaction. So it's not something that will be in your data sheet. It's not something that you can look up in a book. It is something that is different for every reaction, and actually quite a lot of the time we do try and have to work out what the rate constant is. And the units of the rate constant, because this rate is moles per decimeters cubed per second, the rate constant has to have different units to make sure that the rate is in moles per decimeter cubed per second. We will talk about how we work those out a bit later. So we know that square brackets A means the concentration of species A. What does that 2 mean? We can have a look at that sort of squared one. And the squared one is it has an order of 2. So the concentration of A has an order of 2. So if I doubled the concentration of A, it would make sure that the rate of reaction would go up times 4. So the initial rate of reaction would go up times 4. If I tripled it, it goes up by 9. So really, really important. Now, if we look here, we have something with an order of 2 and something with an order of 0. The overall order of reaction is 2 plus 0, so it is a second order reaction. So if our rate constant is equal to, if our rate equals rate constant times concentration of A squared times the concentration of B to the power of 0, concentration of B to the power of 0 is 1. But we can see that if we're looking at our orders, it has an overall order of 2. So how do we work out the units? We know that the unit of rate is moles per decimeter cubed per second. We know that units of concentration are moles per decimeter cubed, and that's it. So K changes. So if I have rate equals K times A squared, we know that the rate is going to have this unit here of moles per decimeter cubed per second. We know that concentration is moles per decimeter cubed. So what we do is we rearrange the equation, we put in the units, and it gives us the units of K. If you have any problems doing that, you can just remember if we have an overall order of 0, units of K is going to be moles per decimeter cubed per second. If we have an overall order of 1, it's just per second. 2 is moles, decimeters cubed per mole per second, and an order of 3 is decimeters to the power 6, moles per to the minus 2, and seconds to the minus 1. Okay, so what is the rate equation and how do we work it out? There are 2 main methods that are used for this. The first is using continuous monitoring. You plot a concentration versus time graph. you use the gradient, which you calculate at various different points, and you have to use your, what do you call them? It's all gone horribly wrong now. Your tangents, there we are. Take tangents at various points along the curve, and from that you can work out what the rate equation is. And you can determine the order. If we use the initial rates method, you do several experiments. You take the initial rates, changing the concentration of certain components. And if you do that, you will be able to calculate the initial rate and look at the effect that changing concentrations has on each part of the reaction mixture. So this is an example. This is for this equation here, which is the bromate ion with a bit of bromide with a bit of acid, making some bromine plus some water. So if we look here, this is a redox reaction. We have bromine, which is in its -6 in a +5 state. This is where we sort of find out I've totally calculated that wrong because it's early in the morning. We have bromide in a -1 state. We've got H plus in a +1 state. We are turning the bromine into 0 state because it's in its elemental form. So we can see that actually we've got a redox reaction happening here. So if I have the concentration of all the initial components as 0.1, it gives us a certain initial rate. Now, that's lovely. It's nice to sort of see that. Doesn't really help us, but if we compare it to if I double the concentration of the bromate ion and keep everything else the same, I can see I double the concentration of the bromate ion and it doubles the rate of reaction. So I can see that actually the rate, which I'm going to call R, is going to equal a rate constant K times the concentration of BrO3 minus, and I can see that if I times it by 2, it times the initial rate by 2, so therefore the order must be 1 because it's only increasing it by the same number of times. So let's have a look at the next one. If I look at this, I've got 0.1, 0.1, 0.1, 0.1, and then we've got 0.1 and 0.3. So I am timesing the BR by 3. And I can see if I times this by 3, because I'm just comparing this one here and this one here, the rate goes up by a factor of 3. So I'm timesing it by 3, the rate is going up by 3. We can see that actually the order with respect to the bromide ion is 1. It's first order. And we've got one more component, which is the H plus ions. So let's have a look at these H plus ions. I have 0.1, 0.1, 0.1. It goes up to 0.2 here. I can see here it's up to 0.2 here as well. So I'm going to compare it with this one here. So let's compare these two. Let's change that. So we can see we've got 0.1, 0.1, 0.1. We've got 0.2, 0.1, 0.1. We've got 0.2, 0.1, and 0.2. So this component here has doubled. So I can see that this has stayed the same, this has stayed the same, this is the only thing that's doubled. So it's 2.4, we've doubled it, and this has actually gone up by times 4. So this has gone up times 4, so that means our H plus concentration, the order of reaction with respect to that is 2. Now, how do we work out what the reaction order is overall? We add this and this and this together, and we can see it is a 4th order reaction. Oh, there we are. It's going all over everything I've written, but we should be able to see that. So what we can do is we can work out what K is, the rate constant for that, by working out what the rate is, and the rate is given to us in the table, so we can use any of those rates as long as we put in the bits of data, and we can work out what K is. K is 12 moles to the -3, decimeters to the power of 9, seconds to the -1. The way we've worked out that unit is by looking at this. So this rate is in moles per decimeter cubed per second, and we divide it by moles per decimeter cubed per second, moles per decimeter cubed, moles per decimeter cubed, and moles squared per decimeter to the power of 6. So that's how we've worked out this concentration, sorry, this K, this rate constant set of units. So if we look at temperature, if we think about it, all of the experiments we've done so far, we've kept everything the same apart from the concentration. If we change the temperature, what it's going to do is it's going to change the rate, and it will change the rate constant. No, it won't change the rate constant. It will, ln K equals ln A minus EA over RT. No, it will change the rate constant. So we are going to study this later on, so don't get too het up by it. But changing the temperature will change the reaction conditions, and therefore will change the rate constant. And if you think about it, if we increase the temperature, because there are going to be more reactions happening, it will increase the rate constant. Please don't read too much into this at the moment, because it is something that we will work through in 18.5. Okay, so these are the key points to remember. If we change the concentration, it can change the rate of reaction. And we can plot how it changes the rate of reaction over time. And some components, if you change them, it will have a non-linear relationship. So it will change it by, for example, a factor of 4 if you double it. And that is called the order of reaction. If some components, if you change their concentration, actually it doesn't affect the rate of reaction. So therefore, their order is 0. As I said, we will be dealing with order a lot more later on, so don't get too worried about it, but it's really important you're able to recognize those graphs. Here is some work for you to do. I've got to say, we don't have the Jim Clark's calculations in chemistry book. They are at the college, but at the moment, obviously, because of the coronavirus, we cannot give them out or anything because we're not there physically. But secondly, bits of paper and things can hold on to viruses and things for a few days. So if any of you do require some extra calculations, I do have some that you can have. Just send me a quick email. Have a look through the booklet. Read through the work as well. Make sure you make those flashcards. And I shall see you soon for another video. I think 18.2 will be presented by Nick. So thank you very much. And I hope you're doing really, really well. I know the college is opening slightly soon. I really look forward to seeing as many of you as possible in there. We will do our best to make it safe for you. So please, hopefully see you next week, I think. So if not, hope to see you soon. We'll carry on doing as much as we can online for you as well. Thank you very much. Bye-bye.